Hello everyone, we are continuing the system properties, and in this video we are going to see the next set of system properties. A system is causal if output at time t only depends on the input at time s, which is less than or equal to t. For the discrete time case, or for the discrete time systems, a system is causal if the output at time n only depends on the input at time s, or at time k, which is less than or equal to n. So the output of a system depends only on the input at time n and the present time and the past samples of your input signal, or past values of your input signal. Right. The first example is the delay system. The relationship between input and output signals of a delay system is y of t is equal to x of t minus t naught, and t naught is a positive number or greater than or equal to 0. So we want to know if it is causal or not. The delay system is the delayed version of the input signal. So you only need to know the past samples of your input signal. So it is going to be a causal system. We can give some numbers to t naught and just check it. So I'm checking it. For t naught equals to, for example, 1, I'm going to have y of t equals to x of t minus 1. Y of t is the shifted version of x of t by 1 point to the right. That means this is the delayed version of x of t by 1 second. If t is a function of second, has the units of, if t has the units of second, this is the 1 second delayed version of x of t. So for example, if I want to know value of y of t at t equal to 0, I need to know the value of x of t at t equal to -1. If I want to know y of t at t equal to 10, I need to know the value of x of t at t equal to 9. At t equal to 10, if I want to know the value of y of t at t equal to 10 seconds, I need to know the value of x at t equal to 9 seconds. So it's the past samples, past values of x of t that I need to find to build y of t. This system is causal, and the output only depends on the past values of x of t, not the future values. Let's look at this integrator system, and I want to know if it is causal or not. All right, so to build y of t, I need to add or integrate x of tau for time points, for tau values from -infinity up to tau equals to t. So I only need to know the values of x of t for all past values of x, up for all of the past values of x of t, for time points from -infinity up to the time point that I'm looking for to calculate y of t. So it only depends on the y of t only depends on the past values of x of t. As a result, this integrator is a causal system. The output only depends on the past values of the input signal. This system is causal as a result. I don't need to know the future values of x of t to build y of t. Let's take a look at this third example. Y of n is x of -n. So I'm looking at this system and giving some numbers for n in this expression. I'm trying to figure out if y of n depends on the future values of x of n or not. In other words, if I want to build y of n, do I need to have access to the values of x of n at time points other than n, or the future time points of n, or just the time point that I'm looking for and the past time points for x of n? So if you give n, like for example 0, you're going to have y of 0 is equal to x of 0, which is fine. It's the present time. To build y of 0, I only need to know x of 0. If I give n equal a positive number like n equal to 1, I'm going to have y of 1 equals to x of -1, which is the past sample for in the sequence of x of n, or the signal x of n. I can go on in the positive with the positive values of positive values of n, and then y of n is always going to be equal to the past samples of x of n. However, if I give a negative number to n, then, for example, if I plug in n equals to -1, y of -1 is going to be equal to x of 1. In other words, to build y of -1, to find y of -1, I need to know the value of x of n at n equal to 1, which is the future value, future time point compared to n equal to -1. So this system is not causal. And a counterexample is this y of n, which is equal to x of 1, y of -1, which is equal to x of 1. That means to find y of -1, I need to know the value of x of n at a future time point compared to n equal to -1. All right, the next property is invertibility in a system. A system is invertible if distinct inputs generate distinct outputs. In other words, a system is invertible if there exists a one-to-one mapping from the set of input signals to the set of output signals. And I can go back and forth between input signals and output signals uniquely. So for any input signal, there is a unique output signal that is related to the output using this invertible system. And if I have a signal at the output, I can identify the input signal that's used to generate this output signal. Okay. To show that a system is invertible, we need to find the inversion formula. That means we need to find an expression that tells me how to calculate y of t or y of n if I have that tells me I need to have an expression that tells me how I can calculate x of n if I have y of n, or how I can calculate x of t if I have y of t, or how I can build x of t using the signal that I have at the output. To show that the system is not invertible, we need to show that two signals map to at the input side map to the same output signal. So I only need to find two input signals that will result in the same output to prove that if you see this output signal or this signal at the output, you cannot tell which one of these two input signals are used to generate this output signal. So there is no one-to-one mapping between input and output in general, and the system is not invertible. Let's take a look at this system. It's defined as y of t is equal to x of 2t. And I want to show that this system is invertible. That means I want to show that if you have x of t, if you have y of t, you can calculate x of t from that. So I'm looking for an expression that tells me x of t equals to a function of y of t. So I can do this manipulation on y of t, my output signal, to generate to get x of t back. So this is what I'm looking for, or a function of y of t. Right. So I know that y of t equals to x of 2t. Let's name 2t as t prime. All right. Then t is going to be equal to t prime over 2. So y of t is actually the same as you write y of t prime over 2. That is equal to, using this expression that you see in here, y of t or y of t prime over 2 is x of 2 multiplied by t, or t prime over 2, which is going to be equal to x of t prime. All right. So y of t prime over 2 is equal to x of t prime. T prime is just a dummy variable. I can name it something else. Let's name it tau if you like. Or you can equivalently use the same t, or let's do an extra step. X of tau equals to y of tau over 2, or I can say x of t equals to y of t over 2. If I have y of t, I can use this relationship between y and x to extract x of t. So I found the inversion formula, and this system is invertible. All right, here is another example for invertibility as a system property. Okay, in this system, y of n is defined as x of n plus y of n minus 1, and we want to know if this system is invertible or not. Okay, if we can find the inversion formula, we can prove that the system is invertible. That means if we can find an equation or relationship that tells us how we can calculate x of n using y of n. So here, I can see x of n here, and the rest are y of n and the shifted version of y of n. So I can write x of n equals to y of n minus y of n minus 1. So there you go. This is my inversion formula, and this system is invertible. Here, y of t is equal to x of t to the power of 2. And I can come up with two example signals, x of t as the whole sequence, that will result in the same y of t at the output. The two signals that I have in mind are x of t equals to -1 for every t, and x of t equals to the constant signal of +1 for every time point. At any time point, x of t is 1. Let's name this x1 of t and x2 of t. If this one goes to my system, y1 of it's going to result in y1 of t. That's going to be equal to 1 for any time point. If this one goes to my system, that's going to result in y of 2, which is going to be equal to 2 for any time point. So if I'm at the receiver end of this signal through my system, and I receive a signal that's equal to 1 for any time point, I'm not going to be able to distinguish between x1 and x2. I'm not going to know if at the sending part, x1 is applied or x2 is applied. So this system is not invertible. A system is time invariant, or TI, if for all inputs x of t and all time shifts t naught, the output to x of t minus t naught is y of t minus t naught. For the case of discrete time system, a system is time invariant if for all inputs x of n and all time shifts n naught, the output to x of n minus n naught is y of n minus n naught. In other words, the response of the system is not time dependent. So if you apply a signal x1 and you receive the output y1, for example, to a system in the morning, the response is going to be the same as if you apply the same input in the afternoon to the system. You are still going to receive y1 at the output of the system, providing that you apply the same input signal. So the change in time doesn't affect the response of your system. The process of checking if a system is time invariant or not is as follows. Step 1, we need to define a new signal, x1 of n, which is going to be equal to x of n minus n naught. This is the shifted version of the original signal xn. We need to find as step 2, we need to find the response of the system to this new signal, or x1 of n. I'm going to name it y1 of n. So if I know the output of the system to x of n is equal to y of n, I'm going to name the response of the system to x1 of n as y1 of n. So if I have the relationship between x and y through my system, I can find the relationship between x1 and y1, or I can find y1 if I have x1 of n. I need to have the explicit relationship between these two of my system. All right, so step 3, I need to find y of n minus n naught, the shifted version of y of n. Then, as the last step, you need to compare y1 of n with y of n minus n naught. If they are equal, the system is time invariant. If they are not, the system is not time invariant. Let's look at some examples and try these steps. Right. I have a system that's defined as y of t is sine of x of t. I want to know if this is time invariant or not. All right, step 1, I'm defining x1 of t as x of t minus t naught. Step 2, I want to find y1 of t, which is going to be equal to, if I know y of t is sine of x of t, y1 of t is going to be equal to sine of x1 of t, and that's equal to sine of x of t minus t naught. All right, good. Next step, I want to shift the output and calculate y of t minus t naught. That's going to be equal to, if I have y of t and I'm looking for y of t minus t naught, I only need to change t to t minus t naught whenever I see t in the expression of y of t. So it's going to be equal to sine of x of, instead of t, I'm going to write t minus t naught. Okay. Now comparing y1 of t and y of t minus t naught, you can see that they are equal. Here, y1 of t is equal to y of t minus t naught. As a result, the system is time invariant. Moving on to the next example, I have a system that's defined as y of n equals to n times x of n. I want to know if it is time invariant or not. Let's follow the same steps. So I'm defining a new signal x1 of n, which is equal to x of n minus n naught. Step 2, I want to find the output of the system if I apply x1 of n. I'm going to name this output y1 of n. That's equal to, and using this expression that I have in here, that's equal to n times x1 of n, because the input signal now is equal to x1 of n. That results in y1 of n. All right. So that is equal to, instead of x1 of n, I'm going to write the equivalent version that I have for x of n. So instead of x1 of n, I'm going to use x of n minus n naught, x of n minus n naught. All right. And now I'm ready to move on to the next step, which is finding y of n minus n naught. Y of n minus n naught, I'm shifting the output. That's going to be equal to n minus n naught. Whenever I see n here, I'm going to change, because I have y of n and I want to find y of n minus n naught. Whenever I see n in here, I'm going to change it to n minus n naught. All right, that's going to be n minus n naught multiplied by x of n minus n naught. All right, comparing y1 of n and y of n minus n naught, I can see that they are not equal. As the last step, I can see that y1 of n is not equal to y of n minus n naught. As a result, the system is not time invariant. All right, the last property of the systems is linearity. A system is linear if it is additive and scalable. A system is additive if whenever you apply x1, you would receive y1, and you apply x2 and you would receive y2. Then if you apply x1 and x1 plus x2, you would receive at the output side y1 of t plus y2 of t. And a system is scalable if whenever you apply x of t and you receive y of t, then applying a times x of t would result in a times y of t for any complex value of for a that you would like. So if applying x of t results in y of t, applying a times x of t would result in a times y of t. If you scale the input signal, the output signal is going to be scaled as well. Suppose the system is scalable. Then if x of t is 0 for any t value, y of t is going to be also equal to 0 for any t value. You can refer to the reference note to see the proof of this property of scalable systems. Now we know that our linear systems are scalable in addition to being additive. So as a result, in linear systems, if input signal x of t is equal to 0 or x of n equals to 0 is applied to the system, the output is going to be equal to 0 or y of t is 0 for any time point, or y of n equals to 0 for any n value. So all zero input signal in a linear system will result in an all zero output signal for these linear systems. So a system is linear if it is additive and scalable. An equivalent condition is that linear superposition holds. That means whenever you apply x1 and you get y1, and you apply x2 and you would get a y2, then if you apply a times x1 plus b times x2, you are going to receive a times y1 plus b times y2 in a linear system. And this expression is valid for any a and b as a complex number. Okay, these are the steps that we use to check for the linearity in systems. First, we need to define x3 of n, which is a times x1 of n plus b times x2 of n. We are building a new signal to test the linearity. Step 2 is to find the output of the system to x3 of n. We're going to name it y3 of n. If I know the relationship between input and output, I can calculate y3 by knowing that I'm applying x3 of n. Then step 3 is to find y4 of n, which is a times y1 plus b times y2. I know y1 is the response of the system to x1 and y2 is the response of the system to x2. Now, at the last step, I need to compare y4 of n with y3 of n. And if they are equivalent, then the system is linear. If not, the system is not linear. Let's do all of these steps for this integrator system. I have, as the first step, I'm defining x3 of t as a times x1 of t plus b times x2 of t. A and b are complex numbers. And next step is to find y3 of t using this expression is equal to integral of negative infinity to t this is x3 of tau d tau. This is the response of the system if I apply x3 of t. That's equal to, I can write it as integral of negative infinity to t. Now, I have the expression for x of t in here, and I want to find the expression for x3 of t. I want to find the expression for x3 of tau. It's going to be equal to a times x1 of tau plus b times x2 of tau, the whole thing, d tau. I can write it as integral of negative infinity to t a times x1 of tau d tau plus integral of negative infinity to t b times x2 of tau d tau. Let's erase these, we don't need them. That's equal to, all right, so I have this one. Let's move on and calculate y4 of t, which is a times y1 of t, this is t, plus b times y2 of t. And I want to check if y3 and y4 are the same thing. All right, that's equal to a times y1 of t is the response of the system if I apply x1. So it's going to be equal to negative infinity to t of x1 of tau plus b times integral of negative infinity to t of x2 of tau d tau. All right, good. Now I can see that y3 of t is equal to y4 of t. And as a result, this system is linear. The second example is a system that's defined as y of n equals to x of 2n to the power of 2. And I want to know if this system is linear or not. I'm going to again follow the same steps and test the linearity. So I'm going to define x3 of n as a times x1 of n plus b times x2 of n. All right. So y3 of n using this expression is equal to x3 of 2n to the power of 2, that is equal to a times x1 of 2n. Okay, if I have x3 of n and I want to find x3 of 2n, I only need to, I'm dealing with this argument here. Whenever I see n, I need to change it to 2n. So plus I have b times x2 of 2n, this to the power of 2. That's going to be equal to a squared x1 of 2n to the power of 2 plus and now you can see that I'm going to end up with the third term here, which is not going to show up in the expression of equation of y4 of n. Let's take a look. This is to the power of 2 plus 2 times ab x1 of 2n multiplied by x2 of 2n. All right, so I have y3 of n. Let's calculate y4 of n. That's equal to a times y1 of n plus b times y2 of n, which is equal to a times x1 of 2n to the power of 2. If I have y of n and I want to find y1 of n, which is the response to x1 of n, I can use this expression here. So the response to y1 of n is x1 of 2n to the power of 2. Now plus b times x2 of 2n to the power of 2. And you can see that y3 of n is not equal to y4 of n. So y3 of n is not equal to y4 of n. And as a result, the system is not linear.